Hello, everyone. First, I would like to start with thanking the organizing committee and the scientific committee for allowing this talk today, and also thank you for hanging in there up to now. And the coming 20 odd minutes, I would like to introduce you in the magical world of Xray CT, which I'm quite enthusiastic about, to be honest. So my name is Bas van Eerdt. I'm founder and CEO of PhenoKey. We're based in the Netherlands. And besides that, I'm also an X-ray enthusiast. And there's one person to blame for that. He's over there. That's Mr. Stefan Geert from Fraunhofer Institute, whom I bumped into 10 years ago on a phenotyping conference. He was presenting a paper with on Xray CT and potato tubers. And then I got hooked and got more and more excited about this technology in the past years. Today I'm also presenting on behalf of some other partners. So that's Fraunhofer IIS from Germany. That's part of the Fraunhofer Gesellschaft, one of the largest research institutes from Europe. And they're dedicated to developing Xray CT hard and software solutions, in this case specifically for the plant and agricultural domain. And also phenoLytics, which is a spin-out from the breeding company Strube, who are the original inventors of the phenotest concept, on which I will present a bit more later. And jointly we are focused and dedicated on developing and integrating Xray CT solutions, applications in the breeding and plant science domain. So let's start with Xray CT. What are we talking about? So it's very basic concepts. You have an Xray CT source that emits X-ray radiation. You have a detector that detects the radiation that passes through the object. We put an object in between, we rotate it, and the resulting beams that are not absorbed by the object are detected by the detector, and that's your signal, and that creates a 2D image. And while doing so, we create somewhere between 600 and 1600 images for every individual scan, which takes somewhere between 2 and, let's say, 15 minutes. It's quite a data beast, so we generate somewhere between 1 and 20 gigabytes per scan. And it's very high resolution. So your average resolution is around 100 micron, but we can also go down to 2 or go higher if possible. Then we have 1000 images. They are in an automated pipeline inserted, automatically reconstructed in a 3D volume, normalized to remove some artifacts that are in there. And then the fun part starts in segmenting the 3D volume for the objects of interest that you're interested in. When these are segmented, then the actual measurement starts, and that is to then measure and write down the trait information and make it available for further research. Why Xray CT? Because it's obviously not the easiest way, technology to implement. It might also not be the cheapest one to do, but I think there are a few pretty convincing reasons to consider it, and I hope to be able to share that with you today. First, we can reveal what's hidden, so you can make things visible that are not visible. Think of roots. What not everyone knows is that Xray CT is actually a biomass measurement. We are measuring biomass. So it's not a proxy, you are measuring biomass, because you measure density, you measure volume, combine the two, you have biomass. And what are we all after? And not in all instances, but in many instances, biomass. And this measures the real biomass. True 3D, so not 2.5D, also not only the surface area, but it's true 3D, true and true. So outside, inside, fully reconstructed, high resolution as mentioned, non-invasive, non-destructive. And we tend to say, and I hope to prove it in some of the next applications, that it's also generating ground truth quality data, which opens a whole new venue of possibilities if you think about it. So today I would like to focus on a few applications, because we promised to show applications throughout the life cycle of plants. First, seedlings, root systems, and also some slides on yield components. First up, seeds. So here you see an image of a container filled with seeds, a few hundred seeds, which is scanned and reconstructed. So it's a 3D volume. From that, individual seeds are being segmented, and from those individual seeds, individual traits are being derived that you see on the right-hand side of the image. So it's about seed code, embryo, size, shape, position, starch position and components, for instance, but also internal defects like insect damage could be detected and quantified. And on the seed lot property, so on the whole batch that you're measuring, you can quantify metrics like 1000 seed weight and biomass. You can also tell something about heterogeneity and the purity of your seed lot. So how many of the seeds in your seed lot are the same type of seeds and how many foreign objects are there, for instance. I bet that not everyone knew that you can measure this amount of traits using Xray CT on seeds. A nice example here. Here you see 3 sunflower seeds. On the outside, they have exactly the same phenotype, essentially. But if you then peel it down and look on the inside, then you see 3 completely different seeds. On the left, you see a well-filled, healthy seed, which will probably germinate well. And the 2 images on the right, they have different types of problems, a necrosis or a broken radical, which might or might not result in healthy and fully developing plants. And so that shows definitely the benefit of looking inside the seeds and not only the outside. And when you do the scanning and when you collect information, with that information you can also tell something about the quality of the seed. So you see well-developed seeds that will generate healthy plants, for instance, and you also damage seeds that might not result in healthy plants. But what you can also see is that, for instance, outside shape or volume of the seeds is not directly dictating whether or not the seed is healthy or not. On the top left, the 2 seeds are both healthy, but one is much smaller as the other, but both show a well-developed embryo, which is probably resulting in a healthy plant. Next up, germination testing. So probably you're all aware of germination testing that has to be conducted, sometimes in soil, sometimes in paper. And in many cases, the paper testing is the method that you have to use, and that's used in all companies. It's all manual, it's very labor intense, it's all done by humans, so it's very subjective and prone to errors. And the result of a trial of 2 weeks with 400 seeds, with people doing all the work, is often not more than 4 or 8 data points. Germinated, not germinated, normal, abnormal, and maybe you do the counting twice. So very little data points for a significant amount of work. So there's a new method available, and that all evolves or revolves literally around this spot. That has been developed by a breeding company, in a breeding company, together with Fraunhofer Institute, and that's what you will see in the next small minute. So this is a fully automated concept of automating the germination trials in vertical pleated filter paper. So this pot contains 50 seeds, and that will be automatically imaged using an Xray CT scanner that you see here in view. All the images are acquired, 3D reconstruction is made, all within the pot, without opening the pot. The paper is removed, the seedlings are isolated, and you have 3D ground truth models of every individual seedling that's in the pot. Those seedlings can be segmented, all the organs are identified, roots, cotyledon, hypocotyle. From every element you know the biomass, the length. When you have multiple time points, you also know the dynamics. So pretty powerful. On the right, the bottom right, you see all the traits that can be extracted. So what can you do with that information? So for instance here, this is just the basic information. So on the left you see normal developed seedlings. In the middle you see abnormal seedlings. And on the right you see non-germinated seeds, obviously. Also the abnormal detection can be done automatically by the software, and that can be configured based on the crops and also preferences of interest that the user has. And by the way, this technology is already in use for 5 years within this breeding company for routine work, for routine screening. So it's not in a lab, it's actually used day to day. Here you see time series. We follow a single seed over time, and you see the plants developing in 3 different seed lots. In the end, the germination count of these normal germination trials will result in the same germination observation. So they're all normals probably, and they're germinated. But you see that there is a completely different dynamic in how they germinate, and that can also be nicely now quantified on organ level, because the bars on the bottom represent the biomass per organ. Also, you can derive a lot of information about the heterogeneity or the homogeneity of your plot, of your seed lot, which is pretty important if you want to sell the seeds to your customers. You want to know how they perform. And here you see 2 seed lots, exactly the same outcome from a traditional germination trial, but here you can clearly see the heterogeneity within the lot, and this can also be quantified in the output data points that you will receive. Vigor. I think the biggest on top of the list of all breeders is if you talk about seed quality and defining quality, is to learn how your seed might perform under stress conditions. And then also vigor is an important thing to quantify that. So here you see 3 different seed lots, again with the same germination performance, but with completely different vigor behavior, which can be nicely quantified because you have all the underlying data points. Another example of what you could do with this is, as you might know, seeds are being treated with fungicides or other stuff to make sure that they perform well in the field. But the formulation of that coating around the seeds can be pretty precarious. You have to be careful in what you're doing because it can help your seeds, but it can also destroy your seedlings at the same time. And there's also multiple effects, so it can maybe boost germination, but maybe it can retard the development of the roots, as you see in this example. So this is an example of different treatments that above ground have similar effects, but below ground they result in a strongly reduced root length of the seedlings, which is important information to take into consideration if you are developing these formulations or if you want to quantify these. One more thing, I always wanted to do this. So we now talked about seeds, we talked about seedlings, but what if we combine the two? Then it gets really exciting. So here we have the pots, we can isolate the seeds. Before germination, we can already look into the seeds and quantify the organs in there, so we know what the seed properties are. Then the seeds are being germinated, and you see the development over time. That's the perfect base for modeling. So you know exactly on seed to seedling basis how a single seed develops into a single seedling. And when you have that modeling, you can also apply that on seed measurements. So you only measure the seeds, and you can more or less predict what the resulting seedling will be. And that can be pretty powerful if you talk about seed operations, where you have to make a lot of steps in the process from receiving the seeds to shipping them, where time is very critical. If you can exactly predict how it will perform, what your quality is, then you can very directly direct your processing steps and also calibrate your machinery to do so. So this is pretty cool, if you ask me. I'm a bit biased, I have to admit. But that was probably already a bit obvious. Another thing you can do with that is learn how what kind of seed traits result in what kind of seedling effect. So here you see on the left-hand side, you see high-quality seeds from all instances, and on the right you see seeds with issues and also the resulting seedlings. And and this is pretty valuable information to know because in seed processing, sometimes seed lots are being sorted by optical sorting or X-ray or fluorescence or whatever. And then it's pretty helpful to know what are your good seeds and what are your bad seeds, and also to make decisions and to program the settings into your processing machine. So you can also use the data to make processing decisions to get the maximum potential out of your seed lots, and also to calibrate the performance of your machinery and to dictate the settings. So enough about seed and seedlings for today. Let's talk about roots. That's a very obvious application, of course, for Xray CT that has been presented upon already a few times here. But it remains a pretty powerful method to extract root traits from plants in pots. So you can do it from pots filled with soil. And of course, there are different soils that will yield different performances. But in general, there's quite a bit of things already possible with different soil types. You could extract information about the roots themselves, the architecture traits, biomass traits, and for instance also elements like root diameter. And again, it's non-invasive, and it's also enabling multi-time point observations. So when you have multi-time point observations, you can obviously track the development of the root system. So here you see an example of a maze experiment where the black images on the bottom are taken on a 7-day interval, where you can clearly see, and again, it's behind it, it's 3D data, and we are looking at a 2D representation, but you can clearly see the increase in biomass over time from the root systems, which can be valuable information. On the right, you see a different data representation with the different time points that have been measured, and there you also see the distribution of root volume over the depth within the pot, which might also yield interesting information. Another example is this experiment with sorghum. So it was a control plant on the left versus a stress plant with limited nitrogen and water. So you can already in the washed root systems, you can see a clear difference in the root biomass, and you also see that represented in the X-ray data that you see in the black rotating movies. but you can also see that the architecture is different, so you can learn a whole lot of information that will otherwise be very difficult to extract when you have to depend on root washing or on other 2D approaches. Yield components. So yeah, that's in the end, everyone wants to learn a lot about yield, and also about yield is affected during the development of plants. So we're approaching the end of the life cycle of plants here. So but this is a nice example, and that was the poster that got me excited, but it's still a nice piece to be able to present. It's on the imaging of potatoes using 3D CT imaging. And here the images are taken in a time course, and it's used to determine the biomass and of individual potatoes in the pots. Measurement time approximately 4.5 minutes. So what can you learn from that? Here you can see on the bottom images the development of the tubers, which is already pretty nice to see how that develops. But it's not only the visuals, it's also the data. So all tubers are segmented individually, and also the biomass of all tubers are quantified automatically in that process. So what you can see on the top graph on the right is that it's correlation numbers between dry and fresh weight. So the fresh weight is what's actually being measured by the X-ray, but with a certain calibration, you can also very accurately, as you can see in this instance, derive the dry weight from that. And on the bottom, you see the tuber weight development over time of the individual tubers within the pots of that have been X-rayed. Next up, wheat ears. Yeah, I learned yesterday that wheat is the dominant crop that everyone's interested in the phenotyping domain, in some kind of poll that was specified. So what's being done, and this is actually an image of the system that's in Adelaide at the Plan Accelerator. And that's being used for doing high throughput measurement of wheat ears in a non-destructive manner. So different wheat ears from trials are being placed in vertical tubes on so-called carriers, around 30 apiece. And those are being scanned automatically in a batch by the PhenoCT, as we call it. In a few minutes' time, the entire object is scanned, and then the individual wheat ears are segmented from it. And then from those wheat ears, we can isolate the individual seeds and seed traits. So here you see what's happening. On the left, you see an isolated wheat ear. Then on the image next to it, you see in colors the different identified seeds in the wheat ear. And if in the middle, you see a representation of all the seeds that have been identified on the wheat ear. And on the right, you see all the parameters that are being extracted from that, which is on spike level or sometimes on single seed level. Again, biomass, shape, and position. And what you, for instance, also can do with that is that you can quantify whether or not seeds have been aborted, or that they have been underfilled, or that they are properly filled. And that can be interesting information to not only specify the number of grains, but also the biomass and the total yield of the crop. And on the left, again, you see that there are pretty strong correlations with drought stress and drought and heat stressed examples. So it's a pretty robust technology that you can use in high quantities. And then the last example, a bit of an odd one. If you talk about yield components, then for trees, wood is the yield. So and the people from Fraunhofer are conducting also field trials with doing CT scanning of mature trees, where you can quantify of course the biomass, but also the type of wood within the tree. So whether it's harder wood or softer wood, that can be nicely quantified using this method. So I hope that the past minutes I could have put these words to the test, and that demonstrated that all that's stated here, that it holds some merits. And if you are getting enthusiasts, which I can of course imagine, then there are different ways to proceed. Then you talk about hardware. There are different elements. You can think about tabletop solutions, intermediate solutions, and large-scale solutions, as you see on the right, which is an example from Purdue University. But together with the partners that I mentioned, we can not only build your equipment, we can also do proof of concept studies, validation pilots, and I can even, in collaboration with Fraunhofer, you can develop completely new methods and equipment if you want to. And I think there's a lot to explore yet in this domain. And maybe one last message is that Fraunhofer Institute is also establishing a new test center that's being constructed by PhenoKey at the moment, which will be ready by the end of Q1 in 2025. And that will be a perfect testing ground for testing out all sorts of different applications for X-ray, but also for other sensor technologies. But Stefan Geert can tell you much more about it. So that's all I wanted to share with you today. I hope I've been able to share a bit of my enthusiasm, and I'm very happy to answer any questions if there might be. Thank you very much.
Ambassador Richard Dick from the IPPN. Just in the field systems, the human safety aspect, I mean, how is that managed?
Human safety, you said?
Yeah, you've got X-rays flying around.
Yeah. Good question. That's the important question. So all devices are intrinsically safe, so they're fully X-ray shielded and protected with interlock systems that mean that the sources will shut down immediately if a door is opened without permission. So the remaining radiation outside of the unit is equal as the ambient radiation.
Bas, my question was about the field systems, like when you
sorry. Apologies.
The operator and so on.
Yeah. So in this case, it is a remote operated vehicle. So this is a very early prototyping stage. So this is more proof of concept on the method, and then it's just by using a certified remote that you can be at a safe distance, that you're not exposed to X-ray radiation. And in the future, that might be and will be implemented in a more intrinsically safe manner, that you can actually drive something and be close to it.
So it's amazing what you can reveal, what is normally hidden. My understanding was that if you do a CT scan one time on an organism, that's quite fine. But if you do it a number of times, you see retarded growth. Yet you show that you follow your plants over time. Have you tested what happens to a plant if you get the amount of doses that you apply?
Yeah, thank you for the question, because that's a question that many people have. Two answers. So you see the example of the breeder Strube. So they are using it for routine screening for the germination testing. And before they made the final call in switching to this kind of testing, they did very rigorous testing to make absolutely sure that there is no effect caused by the X-ray radiation. So that was validated on that way. And in the potato experiment that was also demonstrated, there was also it was a duplicate test. So one set of the plants was regularly exposed to X-ray and the other one not, and there were no visible effects.
Right. So does that mean that there are some species that are more sensitive than others?
We have not observed ourselves any kind of influence on the development of plants as a result of X-ray radiation. That's the answer I can provide you. I cannot provide a empirical answer on that nothing is affected, because we have not tested everything, but everything that we have tested and have been using in X-ray has not shown any kind of effects caused by X-ray radiation.
It's
regarding the germination test seeds, have you ever tried or tested on seeds from a species that has polyandrony species?
Sorry, that has what?
Have you ever tested this equipment on seeds from species that presents polyandrony, more than one embryo within the seed?
Yes, absolutely. So in sugar beets, that's a common. That's where the technology was developed. So multi-germ seeds, if that's what you're alluding to, that's a common thing there, and that can be quantified in these instances. Yes.
We have time for one last question over here.
Thank you.
Quick question. Root imaging. How important is the substrate and the water content in the pot?
Yep. Also, again, good question. Thank you for that. So as mentioned, we can. It's not that you don't have to use artificial soil. So normal soils can be used, but there is that depends, of course, on what the definition is of normal soils. So We have had quite tricky soils where we were able to extract root systems pretty well. But we also, if you have really, really tough soils, then it can be a bit more complex. And additionally, the water content that you mentioned is something that we also see that can affect the segmentation, but it's all about the combination between crop, soil, and water content. But it's definitely important to look at the protocol to make sure that you can get the best results out of it.
I think